Walk through another real-life EKG and talk about some of the fine points of interpreting it, or maybe not so fine. I am just a simple country EMS doc, and so let's hit the high points of it and maybe some of the low points as well. Here's our EKG this time. Take a minute, pause the video, take a look at it, give us an interpretation. Remember, rate, rhythm, axis, intervals, blocks, ischemia and infarcts, pattern recognition, and then do an impression on it. Take a minute, pause the video, and then start again when you feel like you've had a chance to go through it. All right, looking at the interpretation of this EKG again. We're going to start with rate. It does look pretty regular, so we could count the beats or the space in between the beats. But in this case, I always just usually find it easier to count the number of QRS complexes that appear. So we've got, we're just at the tail end of this one. So let's go ahead and call that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Don't quite get to the next one. So it's a 10-second EKG, which they standardly are. Multiply then the number that we have here, so 13 times 6, which is 6 10-second blocks in a minute. That should give you a rate of about 78, which is pretty close to what the computer interprets this as well. The other method works as well. Rate 78, so normal rate. Rhythm, it looks like, looking at especially our rhythm strip, we can see some P waves down here. P wave, P wave, P wave, as we settle out, P wave, P wave, P wave. And looking through all these, looks like every QRS complex has a P wave before it, and each P wave has a QRS complex, and they all basically look the same. So let's call this sinus rhythm. And again, it's a normal rate, so just sinus rhythm at this point. Rate, rhythm, axis. Again, if you wanted to skip something, it could be that, but just to remember, we are positive the QRS is above the line for the duration of it in lead 1. We're mostly positive in V2, so positive deflection, and then positive in lead AVF. Put those three together. We can talk about axis later for what all this means and how you might do that better, but that should give us a normal axis, and in this case, it certainly is. Rate, rhythm, axis, intervals. Let's look at the three intervals that I really kind of care about. One is the PR interval, so let's look for the beginning of the P wave to the beginning of the QRS complex, and that should be less, that distance should be less than one big box, and it looks like it is. That kind of starts on the edge of the second little box. And so certainly finishes before one big box or 5 little boxes. So we'll call this, you may see that a little bit more clearly up here. That space looks smaller than one big box. So we'll call this probably a normal PR interval without even attaching numbers to it. The PR interval, then let's look at the QRS complex, see if it's wide, the distance from the start of the QRS complex, and sometimes you have to look at different leads to really make sure you're getting the start to finish. Start of the QRS complex to the end of the QRS complex should be under 3 little boxes. So that kind of starts on that line 1, 2. There's the third little box, and the QRS complex is not quite finished yet. There's still a little bit more there. This is a bit of a wide QRS complex. So bigger than 3 little boxes makes it wide. And just looking at it, that QRS looks bigger and fatter than you might kind of normally expect. And we can see the same thing if we look at it in V2. Just to confirm, again, our QRS complex starts way back here, and it doesn't actually finish until almost maybe 4.5 little boxes. So not completed under the requisite 3. So this is a wide QRS complex. And then let's look at the QT interval. And again, we're just going to kind of broadly base this as if you start at one QRS complex, is the T wave finished before the equivalent point at the next one? So say we take an R wave here, and then we compare it to the R wave here. Does it look like the T wave finishes before about halfway through that? It does. Halfway would be, somewhere around here. So this looks like a normal-ish QT interval, again, without making any real measurement of it and putting a number to it or calculating that stuff out. Rate, rhythm, axis, intervals. We'll say there's a wide QRS, otherwise intervals look okay. Rate rhythm axis intervals, and then we talk about blocks. So blocks we normally think of when you say block, like an AV block, an AV nodal blocks, and that has to do with the P wave. It looks like all the P waves are consistent, and there's no big changes in the PR interval or anything like that. So there doesn't look to be any block here, and there's good association between the P wave and the QRS complex. So no blocks in terms of an AV side, but what about like the left bundle branch block or the right bundle branch block? And in that's going to be mostly a pattern recognition sort of thing, just based on the evaluation of it. So we do see that there's a wide QRS, which ought to tip us off to say there might be a bundle branch block or some kind of block in here because electricity is not being conducted through the myocardium as fast as it would, and we're going to see that in the QRS complex. So to look at a left bundle or a right bundle, look at V1 and V6 and a little bit in lead 1 as well. But in V1, we see this is a big, fat, negative complex in V1, and it's kind of slurry on this side. It's not real crisp or anything like that. When we look at V6, we see positive deflection and then sort of a little notch, like a little M. And again, it's big, fat, and the second half of it is all kind of slurred into the T wave and then kind of comes out there. When you look at that, and you see that all the way through, you see these big like negative deflections through the septal leads. That's all just the characteristic of a left bundle branch block. Talk about left bundle branch block real quick. Remember, the conducting system of the heart starts you up in the corner of the right atrium. You get depolarization through the atria down to the AV node, where the thing kind of holds on, and then the AV node lets it go. And then you get the QRS complex as it goes through the ventricles. Normally, there's good conducting fibers that transmit that electrical energy fast down through the septum and then out through the ventricles themselves. So that happens pretty quick. So you get a small, a narrow QRS complex. If you put the EKG leads on it and then compare it to what a normal EKG kind of looks like, V1, we'll use V1 and V6 here with the rest of the V leads kind of going in between them. And this is important to note that it is the V leads are facing out of the page at you. It's just hard to kind of depict that normally on a 2D projection. If you look normally, the normal path of conduction is through the AV node here. Initially, here's again the direction of V1, initially away from V1 towards V6, and then quickly turns around and goes back the other direction. In the setting of a bundle branch block, if you take out, say, this left-sided section of this left-sided bundle here, which is on our right, if you were to knock that out, electricity can again go straight through the septum and down through the right side of the heart quickly, but then it will still get to the left side. It'll still get to the left ventricle. You'll get depolarization, but instead of going down essentially a wire, it has to transmit through the ventricle and bleed over onto that left side. So that takes a lot longer, and it initially goes, the path of the electricity is then down, hits the right ventricle, and then has to spread into the left ventricle. And that's why you get that characteristic wide complex QRS. It is a big depolarization that's always essentially going away from V1 because it's always going, from right to left. And it's going toward V6. What you notice on that V6 morphology, though, is that this second peak is this slow part. That's where electricity is coming across the ventricles and eventually depolarizing that left ventricle. That's why it's not like that crisp, clean, straight up, down, that kind of stuff. That may have not made any sense at all, and it's okay if not. The why is not as important as what it is that you're looking for. So again, big, fat, I just think they look kind of ugly complexes that are negative in the precordial leads there and positive with maybe this little notch or this M shape in lead V6. That looks like a left bundle. And in the setting of a wide QRS, that's exactly what it is. So this is a left bundle branch block. Meaning of it, maybe not as important right now, but we'll just stick with left bundle for the moment. All right, left bundle branch block, let's call it that. rate, rhythm, axis, intervals, blocks. How about ischemia and infarct? When you look at this, you may notice that there is maybe a little more ST elevation than you might expect in the precordial leads. Not so much that one, but here you get, almost looks like 3 boxes, maybe a little bit more of elevation there. And you might see that and think, oh my God, that looks bad. That might be a STEMI. And likewise, if you look at V5, you see that we're starting to get some ST depression, and we see that here too. The ST segment is down. Oh my God, is this a sign of ischemia? Look, that's there too. The ST segment is down, is underneath the baseline. And that looks like it's kind of all over the place. And you may say, oh my God, that looks like this could be a STEMI. And it could be still. But the point is that ischemia and infarcts are hard to read in a left bundle branch block because of the enormity of the QRS complex. The thing is that in a left bundle branch block, or in a paced rhythm, or in a right bundle branch block, the ST segment normally goes, in those settings, the opposite direction of the main part of the QRS. So this is V2. If the QRS is mostly big and fat and negative, then the ST segment, the normal response of the ST segment is going to be to go up. And so some ST elevation is okay. That's what we expect it to do, and that's based on the big negative deflection there. So big negative deflection. Likewise, if it's big and positive, then you expect the ST segment to go the opposite direction down. So that's called discordance, and that's appropriate discordance. When you're looking at the bundle branch blocks or a paced rhythm or even LVH, if you have big negative complexes, does the ST segment appropriately change in the other direction? So in this case, what would be pathologic or maybe STEMI equivalent is if the ST segment, while this is a big negative complex, if the ST segment went down. So if you had ST depression here in the setting of this big negative QRS, that would be concerning, essentially a STEMI equivalent. And there's criteria for that they call the Scarbosa criteria. But again, simple me, I leave it as in the setting of the blocks and paced rhythm and that kind of stuff. Whichever way the QRS mostly is, what the most area is, the ST segment should go the opposite direction. And that is appropriately discordant. So positive here, negative ST segment, positive here, ST segment depression. Same thing over in these leads, positive, big positive QRS, a little bit of negative ST change with it, or downward ST change with it, ST depression. So that is actually normal. It is appropriately discordant. Again, if the ST segment went in the same direction as the QRS complex, that's when I would start to get real scared. We can debate about the merits of a new left bundle branch block, by the way, too. But that's how to read, at least to get a better idea of ischemia and infarcts in the setting of a left bundle. It's still very hard to sort that stuff out, but nothing that looks obvious right now. All right, rate, rhythm, axis, intervals, blocks, ischemia and infarct. How about any other pattern type stuff? And I'll just say that we don't see any pattern type stuff. No big hyperacute T waves that we can see. No real peaked like T waves that might suggest hyperkalemia, something like that. So our overall interpretation of this one is going to be sinus rhythm, rate of 78, with a left bundle branch block, an appropriate discordance with no sign of ischemia or infarcts otherwise. So we'll call this sinus rhythm and a left bundle. All right, that'll wrap it up for this one. We'll see you next time. Leave any comments or questions below, and we'll see if we can answer them. Take care. Be safe out there.